the limit of a vector function. So the limit of a vector function R is defined by taking the limits of its component functions as follows. All right, and now this is going to be we're going to call this definition 1, and we'll reference this many times. And basically, this says right here, this definition: if R sub t is equal to, and if it's in a 3D, so we have these real valued function components, so f of t, g of t, h of t, like this. Then, so if we have this, if, then limit, right here, limit as t approaches a of this vector function R of t is equal to the limit of every single component. So limit, this is by definition. So limit of t approaches a of f of t, limit as t approaches a of g of t, and limit as t approaches a of h of t, like that. And I'll just close this off like that. And yeah, this definition is provided the limits of the component functions exist. So all these exist, and then you put them together, you get the limit of the full vector function. Alright, going further. So note, if the limit as t approaches a of the vector function r of t is equal to the vector L, this definition is equivalent to saying that the length and direction of the vector r of t approaches, or actually, this is plural, yeah, so length and direction of the vector approach the length and direction of the vector L. Yeah, so basically, yeah, the size of it, the length of it, and the direction where it's pointing, it's getting closer and closer to L. So equivalently, we could have used an epsilon delta definition. See exercise 1. This is the precise definition of the limit. I will go over that. And here, I'll quickly try to visualize this. I'm just trying to do this off the top of my head. So if we have, this is going to be in 3D. This is going to be a y, z, and x. So let's say we had an L that's like this. Yeah, that's our L vector. Well, actually, technically this wouldn't be a vector. This would be just a, let's say this is the line L. And then let's say it's something like this. And then there's a point right here. And then this point right here is L. This is the L vector at that point, because this defines the whole thing. And then our other vector is it's approaching closer and closer to it as t basically as t gets closer. So let's say we have a vector like this, a different color. And here I'm just doing it off the top of my head. So let's say we have a vector like this. This is r of t vector, and then it gets closer and closer to this right here. It becomes pretty much on this. As it's basically getting closer and closer. And I'll just put it like this. This is r of t as t approaches a. So as t is approaching a, it's going to get closer and closer until it becomes basically flat with this. Like that. Just guys, leave it like that. Alright, yeah, going further. So limits of vector functions obey the same rules as limits of real valued functions. And yeah, basically, see exercise 2. We'll go over the properties of vector functions. Anyways, limits of vector functions. Anyways, continue further. So example 2. This one states, find the limit as t approaches 0 of r of t, where r is a vector, where this vector function is equal to, has components 1 plus t cubed times I vector plus t times e to the power negative t j vector plus sine of t divided by t of this is times by the k vector, like that. That's the ijk. It's just x, y, z component. So solution according to definition 1. So we just apply the definition 1 right here. So we want to know the limit right here, and this is r of t, like that. Yeah. So to take the limit, we just take the limit of each component part. So according to definition 1, the limit of r is the vector whose components are the limits of the component functions of r. Yes, we gotta just apply this. So what I'll do is limit as t approaches 0 of r sub t, or r of t, is equal to the limit, and I'll put this in a close bracket, so limit t approaches 0 of, this is going to be 1 plus t cubed, and this is the I vector, plus limit t approaches 0 of t e sub t j vector, and then the last one, plus limit as t approaches 0 of sine t over t k vector, like that. Alright, here I just made those a bit smaller to fit this in right here. So now what we could do is this equals to, well, just before we get to that, let's just look at, if we plug in 0 inside all of these, we get, we'll do that separately right here. So this equals to limit t, just plug in 0, just becomes just 1 plus 0. That just becomes 1, like that. This is going to be, I'll just put it complete as 1 plus 0, I, plus, now the next one right here, plug in 0. Well, what we get in this scenario, we get a 0. This is e to the negative 0. That's just the same thing as writing, yeah, that's just going to be same thing as writing divided by e to the 0. That's just equals to 1 here by definition. 0 to 1, this just equals 0. Yeah, so then this is just going to, I'll move this all the way to the bottom. And what I'll do is instead of that, this part right here, this is just 1 plus 0. So I'll just put this as 0. Yeah, this is 1. So I'll put this as I, like that. So that's I. This one is this vanishes. This is going to be equal to 0 j. And now the next one right here, this is going to be a sine. When you plug in the sine of 0, 0 divided by 0 is 0. So this is 0 over 0. And this one here, we need to apply the L'Hopital's rule. So I'll put an H like this for the L'Hopital's rule. So this can be plus, and basically it's undefined. So this is undefined. I'll put it like this. Yeah, 0 over 0, undefined. And the whole idea of L'Hopital's rule, yeah, it's basically we take the derivative, and then the whole idea of L'Hopital's rule is to see which one is going to 0 faster. Is it the top one going to 0? If the top one's going to 0 faster, then it's just going to be 0. But if the bottom is, then it's going to go to infinity or a different number. If they're going both similar, if they're going both very, very similar, they could cancel out too. So that's an interesting possibility. So anyways, so limit, this is going to put this in a bracket or like this. This is going to be equals limit t approach 0 and take the derivative of that. This is just going to be d over dt sine t divided by d over t of the bottom. And if we recall the sine rules, this is going to be the derivative of sine is equal to yeah, it just equals to limit approach 0. This is going to be equals to cosine. The limit derivative of sine is just cosine. T, then derivative of t is just 1. Plug in 0 for cosine, that's equals to 1. And this is k, and this is equals to, well, a yeah, this becomes a 1 over 1, so equals 1. So in other words, we get equals I plus k. Yeah, the j vanishes, or you could also write it in a component like this format. This becomes just 1, 0, 1. So the vector is this. The limit as r as t approaches 0 is this vector right here, 1, 0, 1. And now here's just a quick recap on L'Hopital's rule from my earlier video. So L'Hopital's rule: suppose f and g are differentiable, and g prime of x, the derivative of the g is not equal to 0 on an open interval I that contains a, except possibly at a. Suppose that limit as x approaches as x approaches a of fx equals 0, and limit as x approaches a of g of x equals 0, or you could have it going to plus or minus infinity, or the f going plus or minus infinity, or the g going plus or minus infinity. In other words, we have an indeterminate form of the type 0 over 0 or negative or infinity over infinity. Then the limit as x approaches a of fx divided by g of x equals to the derivative. So basically, if it's continuous, Yeah, the indefinite form of 0 over 0 or infinity over infinity. We can just take the derivative. If the limit on the right side exists, or is if then this right here, it equals to this if the limit on the right exists or is infinity or negative infinity. So basically, you can get to infinity, negative infinity, or exist. Or if you have another indefinite form, you can do it again.